All right, today we were gonna run through some problems from homework sets and stuff like that to give us a little bit more experience with the transient analysis before we take our test on Thursday. So with that in mind, the first problem that I would like to work is actually the first problem from homework set 8 because I've been asked a few questions about it. So give me just a moment. Ducks in a row, as it were. So I'm going to be lazy and see if I can just steal this instead of redrawing the circuit. Apparently not. So I got to redraw it. Okay, we'll look at that again. So 2 amp source there. Short circuit goes here. Switch is directed like this. So here's a terminal. Then it goes up. This guy is closing. E is equal to 0, so it's moving from position A down here to position B. Then I have a 5 ohm resistor. $10 microfarad capacitor. $50 and $25. So, and let me check to see what my quantities of interest are real quick here. So there's my voltage and then 3 currents. Okay. Okay, so in this particular problem, before T is equal to 0, the 2 amp source is connected to a network containing a 5 ohm resistor, a 10 microfarad capacitor, and a 50 ohm resistor, all connected in parallel. After the switch is closed, the 2 amp source is effectively removed from the circuit, and the 50 ohm resistor is removed from the circuit as well, leaving behind a 5 ohm resistor, a 10 microfarad capacitor, and a 25 millihenry inductor, all connected in parallel. So this is a parallel RLC circuit. So because it is a parallel RLC circuit during the transient condition, so after the switch is closed, excuse me, we know that alpha is going to be equal to 1 over twice RC. So that would be 1 divided by 2. So what resistor is still in the network? 5. And the only capacitor is our 10 microfarad. Let me grab my calculator real quick. So that looks like, let's see, 1 over 2 times 5 times 10 to the 10 times 10 to the minus 6 is 10,000. Nepers per second. And omega naught is 1 over the square root of LC. So that is going to be our 25 millihenry inductance times our 10 microfarad capacitance to the negative 1/2 power. Close parentheses, to the minus 0.5. 2,000 radians per second. And so we can obviously see that alpha is much larger than omega naught. So this looks like a overdamped circuit. Sorry, I'm having a bit of a brain fart there. So alpha greater than omega naught. So we have an overdamped circuit. Since it's an overdamped circuit, I'm going to go ahead and solve for S1 and S2. So S1 will always be negative alpha plus the square root of alpha squared minus omega naught squared. So that's going to be negative 10,000 plus the square root of 10,000 squared minus 2,000 squared. Negative 202.041 per second. And here I'm going to write C. That's just reminding me of where I've got this stored in my calculator, what variable I'm using, so that when I do calculations later, I'll remember what I'm doing. S2 is negative alpha minus the square root of alpha squared minus omega naught squared. 10,000 minus 10,000 squared minus 2,000 squared. So and that is negative 19,797.959. I'm storing that as variable D. So that would take care of part A for that problem, and then some. So part B asks us to analyze the circuit at T is equal to 0 minus. So at T is equal to 0 minus, again, the 2 amp source is in the circuit. Then we have a 5 ohm resistor in parallel with a 10 microfarad capacitor in parallel with a 50 ohm resistor. So T is equal to 0 minus, our circuit is going to effectively be this guy. So we have our 2 amp source feeding a 5 ohm resistor through which there is some current IR at 0 minus that we may need to pay attention to. Since we're before the switch has changed states, we are at DC steady state, so the capacitor is going to look like an open circuit. Here is our 50 ohm resistor. And then just for the sake of argument, this is where my inductor would be, but it's not actually connected at that topmost terminal. Here is IL at 0 minus. Here is IC at 0 minus. And this is as good a place as any to measure V at 0 minus. So let's just identify all 4 of those quantities for the heck of it. Bless you. So what should our voltage at t is equal to 0 minus be? Okay, so you use current division and then found the voltage drop across the 5 ohm resistor. That is literally identical mathematically in every way to just taking that 2 amps of current and multiplying it by the equivalent resistance. So I'm going to use Ohm's law because it gets the exact same result in 1 step instead of 2. So that would be 2 amps. And then we're going to have 5 ohms, 50 ohms, 5 ohms, plus 50 ohms. And I want to say that's like 9.09, but I'll double check. So 5 times 50 is 250 over 55. 100 over 11, yep, 9.091 volts. Then we have, let's do IR, 0 minus. So I can see why you did current division now, because that got you that current directly. I'm going to go the other way around. It's just going to be V divided by that 5 ohms, right? So 9.091 volts divided by 5 ohms gives me 1.818 amps. IC, or let's do IL. So RL and then C. By inspection, the inductor current has to be 0. And then finally, we have IC at 0 minus. And by inspection, that guy has to be 0 as well, because no current can flow through either of those open circuit connections. So our analysis at t is equal to 0 minus is complete. Now let's look at this guy at t is equal to 0 plus. So we know that the so at t is equal to 0 plus, let me scroll up here and look at our original circuit. The 2 amp source has been removed from the network completely because the way that that switch operates is the 2 amp source is now connected to that short circuit. And so we're just going to have a circulating current there that's going to be disconnected from the RLC network. The 5 ohm resistor is going to be in parallel with the 10 microfarad capacitor. The 50 ohm resistor is effectively removed from that network, and the 25 millihenry inductor is switched in. So I'm going to replace my 10 microfarad capacitor with a voltage source. Okay. So at this specific moment in time, what we have is our 5 ohm resistor doing what it needs to do. Here's IR at 0 plus. We have our capacitor, which we know has a fixed voltage of 9.091 volts across it. and a potential current of IC at 0 plus flowing through it. Our inductor is switched in. However, our inductor is going to be acting as a current source because it has a fixed amount of current, 0 amps flowing through it. So we know for sure that this current IC at 0 plus, or excuse me, IL at 0 plus has to be 0 amps. IL. There we go. And we know that our voltage V at 0 plus has to also be 9.091 volts. That is because the voltage drop over a capacitor cannot change abruptly, and the current flowing through an inductor cannot change abruptly. So let's just write all that stuff down. V at 0 plus is equal to 9.091 volts. IR at 0 plus is going to be what? 9.049 divided by 5, right. So 9.091 volts over 5 ohms is going to give us 1.818 amps again. Then we'll have IL at 0 plus, which we know has to be 0 amps. And finally, IC at 0 plus, what's that going to be? Negative IR, all right, so negative 1.818 amps. All right, on this particular problem, I didn't ask you to analyze the circuit at t is equal to infinity. Why?
Because our infinity values would be 0 anyway.
Yeah, all of them are going to be 0 because there is no independent sources left in the circuit whatsoever at t is equal to infinity. So nothing will be influencing the behavior of the circuit. So we can say that it is 0 by inspection and not waste our time doing that analysis. So now we will need to determine, use our table and figure out what our coefficients are. What quantities exactly was I solving for? We'll talk about that. So I want the voltage and the capacitor current. All right. So I can say that V of t will be of the form A1e to the S1t plus A2e to the S2t. And I don't have to add my infinity term because I know that it's 0. So it's of this form because the circuit is overdamped. At t is equal to 0, so V of 0 plus is then going to become A1 plus A2. So I can say that A1 plus A2 is equal to 9.091 volts. This is my first equation. Easy peasy. Now I'm going to use my derivative-based relationship, so I can say that IC of t is equal to C dV by dt, which is then going to be C S1C A1 e to the S1t plus S2C A2 e to the S2t. At t is equal to 0, this reduces to S1 C A1 plus S2 C A2. And so for my C value of 10 to the minus 6, this is going to look like, let's see, S1 I saved as C times 10 to the minus 6. Negative 2.020 times 10 to the minus 3 A1 minus 1.97 away thing. Sorry. I don't want to expand, clear this, go away. There we go. 1.9797, so I guess 1.8980 times 10 to the minus 1. A2 is equal to my capacitor current, which was negative 1.818 amps. So there is equation 2. I can now solve this system of equations for A1 and A2. I'm going to put these rounded versions of stuff in, so it's not going to be exactly correct, but it'll be close enough for me. So my coefficients for my first equation, I have 1A1, 1A2 is equal to 9.091. My second equation, I have negative 2.020 times 10 to the minus 3 A1 and negative 1.980 times 10 to the minus 1 A2 is equal to negative 1.818. Solve. I get A1 is equal to negative 0.092 volts, which would be the same as negative 91.754 millivolts, and A2 is equal to 9.183 volts. All right. So does that what you guys got? Let's start there. Did you solve the system? Okay. All right. So from this, we know that V of t is just going to be negative 91.754 e to the negative 202.041 T millivolts plus 9.183 times e to the negative 19,797.959 T volts, because we can just directly apply the coefficients A1 and A2. For our capacitor current, we can see pretty easily that we're going to have to multiply S times C times A1 to get our first coefficient, and S2 times C times A2 to get our second coefficient. So I'm going to go ahead and do that in my calculator. So let's see, that's going to be the variable that I have stored as X times the variable that I have stored as C times 10 to the minus 6 So that's going to look like 185.381 e to the negative 202.041 t microamps there. And then for my second term, where I have S2, which is D times C, so 10 times 10 to the minus 6 times A2, which I have stored as Y. I get negative 1.818 e to the negative 1970 7.959 t amps. Obviously, there's a little bit of rounding error and stuff in here because I didn't use the exact numbers and all that kind of stuff, but this should be close to your answer. So this analysis makes sense. So let's start. The first thing, could you guys see that it was a parallel RLC circuit? Okay, that's an important step because that's going to save you a lot of time going through the general thing that you don't need to do. Determining the initial conditions on the system, how was that? Because I had a little bit of questions about that through email and all that kind of good stuff.
I think that's where I started.
Okay. All right. After that point, using the table is just kind of using the table. So really, yeah, the biggest thing is determining the initial conditions correctly, and then everything past that critically depends on getting those numbers right. If you don't do it, then everything else kind of falls apart pretty easily. Any other questions on this particular problem?
For your ICT, you just multiply your S1, C, and A1 together?
Yeah, so if I look at this equation right here, let me put a box around it. All right. I know that my capacitor current, by definition, is just C times the derivative of my voltage. And so the derivative of my voltage bit came directly from the table. That's S1 A1 e to the S1t plus S2 A2 e to the S2t. And then I distributed my capacitor value C. So I can see that the coefficient for the e to the S1t term is just the product of S1, C, and A1. So that's all I did. Let's just multiply those three guys together. Same thing for the coefficient for the e to the S2t bit. I can see that that is multiplied by a factor of S2 times C times A2. So I just multiplied those three numbers together, and that is exactly where this guy and this guy came from, respectively. And it should match our initial conditions on the system, right? So I know that my current should be negative 1.818 at t is equal to 0, right? So I have this guy right here, microamps, so it's really, really small. And then I have this negative 1.818 amps, so that's where that came from, right? So it matches my initial condition. Similarly, on the voltage, I know that I should have 9.091, while I have 9.183 minus 0.09 volts. So it's going to match that 9.091 as well. So if my initial conditions are matched, and I calculated S1 and S2 correctly, then I'm good to go. All right, so the next problem that I want to take a peek at is this ugly guy right here from a homework set that I'm going to be assigning to you today because I forgot to do it yesterday. This one in particular will take a little bit of explaining to do because it has a dependent source thrown in the mix and all that kind of stuff as well. So let's just write it down and start looking at what's happening. 1 farad, 3 Henry. -2 IA, positive polarity on top. All right, so this switch is doing like this. This is A, this is B. It's occurring at t is equal to 0. Go away, emails. Then let's see, what's what. So VR, VL. And let me write down what our ultimate goal is, figuring out what IA is. All right. Okay, so let's talk about what type of circuit this is. Any thoughts? Series, why?
I was gonna say series because the capacitor and the inductance are.
Okay, so the capacitor and the inductor are definitely in series. Is there a resistance in series with this? Because it's got to be all series.
Can you combine two resistances after?
All right, so the question is, can I combine the two resistances? So when that switch closes from position A to position B, that places the 1 ohm resistor in parallel with the 3 ohm resistor. So I could make a combination there. But what do I do about that dependent source? All right, no. Also no. All right, so let's think about what we're inherently looking for in these circuits, right? We're looking for an equivalent resistance, an equivalent capacitance, and an equivalent inductance, right? So the equivalent resistance is what's seen during the transient condition if we take the inductor and the capacitor out. So during the transient condition, I'm going to have my 3 ohm resistor like so, that is in parallel. Actually, it doesn't really matter because they're in parallel, but I'll have my 1 ohm resistor here on the left, my 3 ohm resistor here. Then I will have a dependent source like so, having a value of -2 IA. This is the terminal where my bottom leg of my inductor is connected. And up here, this is the terminal where the left leg of my capacitor is connected, right? Let me specify where IA is. So let me ask you guys a question. Do we have the skills to determine the equivalent resistance of this network? If so, this is a series RLC circuit. If not, it isn't a series RLC circuit.
You can find
So we just want effectively the Thevenin equivalent resistance of this network, looking into that open circuit set of terminals. Is there a independent source here at all? No. So we're going to have to use a test source method to do it. Right? So would you guys prefer to use a test current source or a test voltage source? Voltage, okay. So I'm going to apply a test voltage source across the terminals of my network. And I'm going to say that V test will be 1 volt. And I arbitrarily chose the top polarity to be positive, but it wasn't particularly matter. That means that I'm going to have to find some test current, I test, that is leaving the positive polarity terminal, and the ratio, so Req will by definition be V test divided by I test, right? That's how we apply the test source method to determine the equivalent resistance of any network containing a dependent source, right? Okay, so what analysis method do you guys want to use to determine what that current I test is? Nodal, okay? Okay. So mesh or nodal, both of those are perfectly applicable. I'm going to choose to use mesh analysis. The reason being is that I'm looking for a current, so I'm going to use the method that solves for currents. So let's define this guy right here as mesh current I1, this guy right here as mesh current I2. And I don't have any current sources in this guy whatsoever, so this is just going to be 2 KVL equations and then I solve them, right? So starting for mesh 1, I'm going to see 1 ohm times I1 plus 3 ohms times I1 minus I2 is equal to 0. Everybody okay with that? Then going around mesh 2, I'm going to see 3 ohms times I2 minus I1 plus 1 volt plus negative 2 IA is equal to 0. So now I need to write an equation for my controlling variable IA in terms of my mesh currents. Bless you. So IA, it has what relation to our mesh currents? I disagree. I1 minus I2, right? Because IA is in the middle, it's got 2 different mesh currents flowing through it. I1 is flowing in the same direction, so it gets positive sign. I2 is flowing in the opposite direction, so it gets the negative sign. And I'm going to solve this system for I1, I2, and IA. So I'm using IA as a variable so I can be lazy and not have to do substitution and potentially make a dumb algebraic mistake, because I do that fairly often. Sorry. So in my first equation, I have 1 plus 3 is 4I1, negative 3I2, and 0IA. In my second equation, I have, sorry, and this is all equal to 0. In my second equation, I have negative 3I1, positive 3I2, negative 2IA, And when I move that 1 over, it's going to look like -1. In my third equation, I have 1I1, -1I2, -1IA is equal to 0. Solve, and I get I1 is equal to -3/5 of an amp. I2 is equal to -4/5 of an amp. And IA is equal to 1/5. So what does I test? Negative I2, right? Because it's representing the same current but flowing in the opposite direction as I2. So that will be 4/5. Goodness gracious. Of an amp, which means my equivalent resistance is 5/4 of an ohm. Right? Because 1 over 4/5 is 5/4. So from that, because we have a series RLC circuit, because we now know that we can treat that network as just a resistor in parallel, or excuse me, in series with that inductor, which is in series with that capacitor, we know that alpha should be R EQ over twice L. So that'll be 1.25 ohms over twice 3 henries. So 1.25 over 6 is 0.2083 repeating neppers per second. Omega naught is 1 over root LC. It's going to be 3 henries times, was it 1 farad? Yeah. It's the square root of 1/3, which is 0.577 radians per second. So we can see that omega naught is greater than alpha, which means this circuit is underdamped, right? Since the system is underdamped, I'm going to go ahead and calculate omega D. So omega D will be the square root of omega naught squared minus alpha squared. So that looks like 0.577 squared minus 0.208 squared. So something in the ballpark of 0.538 radians per second. All right, so now we have to analyze the circuit at t is equal to 0 minus, analyze the circuit at t is equal to 0 plus. But I want to look up at this guy real quick because we have to think about things here, okay? Our ultimate goal in this problem is to solve for that quantity IA of t, which is the current flowing through the 3 ohm resistor, all right? Current flowing down through the 3 ohm resistor. So what quantity are we going to be using to try to determine that? And so what I mean by that is, should we be looking for, say, the capacitor voltage or the capacitor current or the inductor voltage or the inductor current? What's going to be the easiest path by which we can determine that current IA at the end? Because our methodology that we've developed is for solving specifically for capacitor voltage, capacitor current, inductor voltage, inductor current. So we're going to have to solve for one or more of those quantities and then use those known values and our basic circuit analysis techniques like KVL, KCL, etc., to figure out what IA is. So how would you guys, like, what quantities need to be known for us to figure out what IA is?
I would say current through the inductor.
Okay, so if we determine the inductor current, which I've represented as I of t, that's also happens to be the capacitor current because they're in series. We could use that to determine IA. I agree, but how?
KCL at the top.
So if we did KCL at the top node, we knew the current flowing to the right. We would also have to know the voltage drop over the resistor in order to get that the current flowing. In order to apply KCL at that topmost node, this guy right here, and determine that current IA, we would wind up having to know the voltage drop over that resistor, which is labeled as VR of t. I think that we can use just that current I of t like you suggested, but approach it in a slightly different way where we don't have to determine that voltage. So what I mean by that is the same current I of t is flowing through the rest of those elements in series, and it sees a 3 ohm resistor in parallel with a 1 ohm resistor. So I would argue that we have a known amount of current, because that's what we're going to be solving for, flowing into a parallel resistor network, and we just want to know the current flowing through one of the resistors. Sounds like we should be using current division as the most efficient way to determine that. It's by no means the only way to do it, but it is the most efficient way. Does that make sense? Right? So to avoid having to get some relationship for figuring out what that voltage VR is, which would wind up, we would have to do KVL around the right-hand loop, which means we'd have to know not only that current I of t, but also the capacitor voltage VC of t and the inductor voltage VL of t. We can solve for it directly using current division. So that's the approach that we're going to take. So this begs another question. Do we have to analyze this circuit, or can we analyze the electrically equivalent circuit where we are only paying attention to that resistor network and the dependent source as a 5/4 ohm resistor?
We can until we have to solve for IA.
Exactly right. So we can simplify this guy down to solve for I of t and then go back to the original circuit at the end. And there's nothing wrong whatsoever in doing that. All right, so we can treat it that way specifically at t is equal to 0 plus only, though, because that only behaves, that 1 ohm resistor in parallel with a 3 ohm resistor in series with that dependent source is, we determine the equivalent resistance during the transient condition. So at t is equal to 0 minus, we have to look at what this guy is doing as a whole, because we don't know how that portion of the circuit behaves. Does that make sense? So The simplification that we have developed is only valid during the transient condition. So if we're looking at the circuit before the transient condition happens, it is invalid. All right. So at t is equal to 0 minus, let's see what's this guy going to look like. We're going to have a 10-volt source in series with a 1 ohm resistor. Here's a 10-volt source. Here's our 1 ohm resistor. Here is our 3 ohm resistor through which our current IA at 0 minus flows. Because we're at DC steady state, our capacitor is going to look like an open circuit. Our inductor is going to look like a short circuit. And then we have our dependent source having a value of -2 IA at 0 minus goes here. Here is our current IL, I at 0 minus. Here is our voltage, VL at 0 minus. And this is our voltage. Give myself a little bit more room here. VC at 0 minus, okay? All right, so let's take care of some low-hanging fruit first. It should be fairly obvious that I of 0 minus is 0 amps, because that represents the current flowing through the capacitor, which is 0 because it's an open circuit. So that guy's pretty easy. Another easy thing to determine is the voltage drop over our inductor at t is equal to 0 minus. So at t is equal to 0 minus, the inductor is represented by a short circuit because we're at DC steady state. By definition, short circuits have a voltage drop of 0 across them. And we have ran out of easy things. So our only other real quantity of interest here that we have to pay attention to is our capacitor voltage at t is equal to 0 minus. That's going to be a little bit more difficult to determine, right? So VC at 0 minus. Any thoughts on how we might calculate that?
Find the dependent voltage source value.
Okay, so we're going to have to find the dependent voltage source value. So I'm going to label some things here real quick, just for the heck of it, all right? I'm going to call this guy node A, and this guy node B. And so we could see that VC is just going to be VA minus VB for sure, right? So VB is the dependent source voltage for sure. So let's come over here. So VB is equal to negative twice IA at 0 minus. That's going to be -2 times what? How do we find that current IA?
We have the 10-volt source.
Okay.
In series with the 1 ohm and 3 ohm resistor.
Okay, so 10 volts divided by 1 ohm plus 3 ohm is going to give us -5 volts, if my mental math is correct. -20 over 4 is -5, yeah. Okay. how do we get VA? Voltage division, okay, that's fair. So 10 volts times 3 ohms over 1 ohm plus 3 ohms is 7.5 volts. I'm on board with that. So what is VA minus VB then? 12 and a half. All right, so this guy is analyzed at t is equal to 0 minus. At t is equal to 0 plus, now we can replace that ugly network with just a resistor, right? So effectively, we are going to have our resistor, which looks like 5/4 of an ohm connected to our capacitor, right? So our capacitor would go here. I'm going to lightly pencil it in and we're going to erase it in a second. And then our inductor would go here, where I'm going to try to lightly pencil it in and we'll erase it in a second. And our current I at 0 plus is the one flowing around that loop. Our voltage VC at 0 plus is this guy. And our voltage VL at 0 plus is this guy. So what should we be replacing our capacitor with? Let's start there. Pardon? 12.5 volt source. Positive polarity on the left, negative polarity on the right. So that's our capacitor right there. We know that VC at 0 plus has to be 12.5 volts. What are we replacing our inductor with? Pardon? So we know that we have a current of 0 amps, right? Open circuit, absolutely right. So we want to force the inductor to carry 0 amps, which means we need to replace it with an open circuit. All right. So we know that I at 0 plus is equal to 0 amps. Both of those we got because we know that the current through an inductor cannot change abruptly and the voltage drop across the capacitor cannot change abruptly. So our last quantity that we're going to need here is the inductor voltage, VL. What is that going to be? Negative 12.5 volts. Absolutely correct. So we can see, sorry. Come on, there we go. Negative 12.5 volts. All right. So we can see that it's got to be negative 12.5 volts because there's obviously going to be no current flowing through that equivalent resistance because it's not part of a closed current carrying loop. And so VL of t represents the exact same voltage as VC of t. They just have opposite polarities. All right, so we've analyzed the circuit at t is equal to 0 plus as well. So we are done with the determining our conditions and all that kind of stuff. Now it's time to go to the table because this is obviously obviously at infinity, everything is going to go to 0 because there are no independent sources forcing it to behave otherwise. All right, so our goal here is to figure out what I is. Because we know that we can use that to determine IA. So I of t will be of the form B1 cosine omega dt plus B2 sine omega dt, this whole thing multiplied by e to the negative alpha, sorry, e to the negative alpha t. I was trying to remember if alpha was negative or not. Like it had an actual negative value. It does not, but I know that this thing is going to exponentially decay. So I at 0 plus just looks like B1, right? Because cosine of 0 goes to 1, sine of 0 is 0, and e to the 0 is also 1. So we just have 1 plus 0 times 1 is, or B1 plus 0 times 1 is B1. So from this, we can say that B1 is 0 amps. All right, so that's easy enough. Then we have our voltage relationship. VL of t is equal to L di by dt is going to be, oh gosh, let's see. I think it's omega d B2 minus alpha B1 cosine omega dt minus omega d, sorry, B1 plus alpha B2 sine omega dt e to the negative alpha t. Please, if you have your sheet, look and make sure I didn't screw that up. Awesome. My memory is a steel trap when it wants to be. All right. So VL at 0 plus is then just going to be L times omega d B2. And that's it, because we know that B1 is 0. So this looks like B2 is equal to VL at 0 plus, which is negative 12.5 volts divided by L, which was 3 henries, and omega d, which was 0.538 radians per second. So that's going to be negative 12.5 divided by 3 times the variable that I've stored as x, negative 7.7417, so 742. This thing will write amps. From this, I of t is going to be equal to negative 7.742 sine omega d, which is 0.577 t e to the negative 0.208 t And now we have to figure out what IA of T is, right? So let's go all the way back up here and look at what we're going to do. All right. So I of T sees that 3 ohm resistor in parallel with that 1 ohm resistor, right? So I would argue that 1/4 of I of T is going to flow up through the 3 ohm resistor, and 3/4 of I of T is going to flow to the left through the 1 ohm resistor, based on how current division works, right? We could more formally do it, and I'll probably do that in just a second. But also I can see that IA is flowing in the opposite direction of what I should expect to see using current division. So that in mind, IA is going to be negative IT multiplied by 1/3 over 1/1 plus 1/3, which let's see, so that's going to be 1/4. So negative I of T over 4. So that's going to look like positive 1.935 sine 0.577 T e to the negative 0.208 T amps. That guy was a little tricky because of that dependent source. But I'm not going to give you any problems with a dependent source that doesn't reduce down to a simple parallel RLC or series RLC. So just, you got to figure out what the equivalent resistance is correctly and then run from there. All right, so we technically only have 4 minutes left of class, so give me 4 minutes worth of questions. If you got any.
What's the best way for me to like read up on transient analysis?
Do the homework. Yeah. Do the homework, and then so as part of every homework problem, the last thing that I ask you to do is simulate it, right? So you know whether or not you did it right when you simulate it, and the expression that you type in exactly matches the expression that the simulation gives you.
Yeah. I wanted to like get better at finding condition.
So you can simulate those too, actually, right? So that's just DC circuit analysis. So just do a DC operating point. So set up the circuit the way that you believe it's supposed to be. So like at T is equal to 0 minus, replace all of your, let's see, yeah, replace all of your capacitors with open circuits, replace all of your inductors with short circuits, or it might be better to do 0 volt voltage sources in your, in your simulation. And the reason why I say replace your capacitor, your inductor with a 0 volt voltage source as opposed to a short circuit is because LT Spice won't tell you the current flowing through a wire, but it will absolutely tell you the current flowing through a 0 volt voltage source. And so you can see whether or not you got the current correct that way, and you can see whether or not you got the voltage over your open circuit by just taking the voltage drop across the 2 nodes. And then you could do a similar thing for T is equal to 0 plus, making sure that you replace your current, you replace your inductor with a current source having the value of the inductor current at 0 minus, and you replace your capacitor with a voltage source having a value of the capacitor voltage at 0 minus. And then it's just another DC circuit. So throw it into LT Spice as a DC circuit, and then make sure that what you get matches what the simulation gives you.
For number 4 on the last homework, it also has a dependent source.
Right.
It's that one.
Uh-huh.
Can we just, when we're finding like R and Q, would it just be those two in series, or would we have to do another analysis? Like how?
You'll have to do it. So the 7 ohm resistor is in series with the 2 ohm resistor, but is also in series with that dependent source. So you're gonna have to do a, whatchamacallit, the test source method as well.
Okay.
Yeah, because it's gonna look like 9 ohms in series with that thing, but it's still in series with a dependent source, and you don't know what the resistance of the dependent source looks like without doing a test source method. So you absolutely can't just say it's 9 ohms and go from there. All right. So I know that homework, whatever this one was technically due yesterday. I'm going to extend it until this Friday to give you guys more time to mess with it and all that kind of stuff, because you may need it. So if you've already submitted it, you can, if it will allow you to, delete your submission if you want to go back and rework some stuff, or just shoot me an email and I'll delete it for you and allow you to re-upload. Sound good? All right, I'm gonna actually get those homeworks put up like right now because I don't have a meeting immediately after class, which made me forget about crap. So unless you guys got anything else, I'll see you. I won't see you Thursday because your test will be posted online and you're gonna do it from home. So